Now, what if you're given multiple sets of conditions? So it gives you an original set of pressure, volume, temperature conditions, and then it says we change the pressure to this or something along those lines. And asks for a new volume or a new temperature. Any kind of a problem like that, basically what we need to do is we need to start with two different ideal gas laws. So we have an ideal gas law for the first set of conditions. So I'm giving it a subscript 1 for each of the variables, except for r, because that's a constant, so that does not change. And that just means in your first set of conditions, the pressure, the volume, the number of moles, and the temperature. I'm going to write an ideal gas law for a second set of conditions. Now, algebraically, if we were to solve for r, we'd have to divide both sides by nt. So we can say that P1 V1 over N1 T1 equals r. And likewise over here, P2 V2 over N2 T2 is equal to r. Remember, these r's, since it's a constant, are the exact same value. So if this whole thing here is equal to a constant, and this is equal to that exact same constant, they're also going to be equal to each other. So, let's write that. Let's show them being equal to each other. So we can say P1 V1 over N1 T1 equals P2 V2 over N2 T2. So this is a version of the ideal gas law you can use if you have changing conditions. And what's nice about this is that you can just pick out whichever variables you need. So for instance, let's say we have a problem where it says you start with a pressure of 2 atmospheres and a volume of 5 liters. What happens to the volume when the pressure is decreased to 1 atmosphere? Any of these variables that are not mentioned in the problem, you can assume they stay the same. So in this case, the number of moles and the temperature were not mentioned, so we can assume they stay the same. So pressure and volume are what's mentioned. So we'll just basically pluck those out of this equation and use them. So we can effectively cover up the n's and the t's and just write what we're left over with, which in this case is P1 times V1 equals P2 times V2. P1 is going to be 2 atmospheres. V1 is 5 liters. P2 is 1 atmosphere. And of course we're solving for V2. And we do the math here, and we get 10 liters equals V2. And just to double check, I mentioned that according to Boyle's law, we learned that pressure and volume are inversely related. So in my original problem, the pressure went down, right? And in fact it went down by a factor of 2. So my volume should have gone up by a factor of 2, since that was the only other thing affected, and in fact it did. Let's do one more example. Let's say we have, let's say we're given initial conditions of a pressure of 5 atmospheres, a volume of 20 liters, and a temperature of 300 Kelvin. Let's say our final conditions, so these are the conditions that our gas starts with, and let's say if the pressure goes to 3 atmospheres and the volume goes to 15 liters, what is the new temperature? Well, in this case, we're talking about, we use pressure, volume, and temperature. So the only thing we can cover up is the number of moles. So we just have to take the rest of the equation exactly the way it looks. So with temperature being in the denominator there, we have to leave it in the denominator. So we'll say P1 times V1 over T1 equals P2 times V2 over T2. So from here we can just plug it in. P1 is 5 atmospheres. V1 is 20 liters. T1 is 300 Kelvin. P2 is 3 atmospheres. V2 is 15 liters, and we're solving for T2. Now, one thing to keep in mind, we cannot just solve for this and then divide this number over and get T2, because T2 is in the denominator here. So if we did that, if we just solved this and divided this number over, we'd be solving for 1 over T2. So algebraically, we actually will need to get T2 in the numerator before we can get our final answer. But to make that algebra a little bit simpler, first I'm going to solve this, and I'm going to solve this to get less numbers involved with everything that is going on. So 5 times 20 is 100, divided by 300, of course, gets us 0.33 repeating. So that's equal to 3 times 15 is 45 over T2. So now we can algebraically, let me show this in another color, we'll multiply both sides by T2, because whatever you do to one side, you have to do to the other to keep them equal. Right? So here, T2 divided by T2, that cancels out. So we get T2 times 0.33 repeating equals 45. So now, just divide both sides by 0.33. And we get 135. Right? Okay, and we get 135. You didn't be Kelvin still, and that would be our final answer. And again, anytime you have changing conditions, this is just the way you're going to be able to solve it. Again, just pick out whichever variables are actually being used. And there's just one more version of the ideal gas law that I want to discuss. So if we're starting with the primary version, so this will bring into account the density and the molecular weight, because sometimes you'll be given those values. So density, actually, first algebraically I'm going to change this around a little bit. So I'm going to divide both sides by basically nRT. Right, so we've got PV over nRT equals 1. And now I'm going to just divide both sides further by V. And you'll see in a moment why I'm doing this. So the V's cancel out here, and we get P over nRT equals 1 over V. Okay, so density, hopefully you remember, is the mass divided by the volume. So we can basically, if we just multiply both sides by mass, we get M times P over N RT. And here we have M divided by V. Well, I just said that's the density. So this is, I guess we can actually get two versions out of this. So here is a third version of the ideal gas law. Mass times pressure, divided by the number of moles, times the gas constant, times temperature, is equal to the density of that gas. However, maybe you'd recognize this as well. M over N. That's the mass divided by the number of moles. If grams divided by moles sounds familiar, that's good, because that is the molecular weight, or the molar mass. So we can actually substitute that out, and we could say the molecular weight times the pressure equals, or divided by RT equals the density. So you can actually use these values to find the molecular weight of an unknown gas. And that is the fourth and final version of the ideal gas law.